Log on, tune in, find out. Another good idea from Cambridge.
Homogenized hybrid particle fields. Thank you. Thank you for the organizers for inviting me to give this presentation. This is to do with multi-scale dynamics and information. It is regarding new homogenized particle filters that we have developed. This joint work with June Park, who is now in Brown, and Yoon, and my colleague Richard Charles. I'm from aeronautics. I'm not a climate person. I'm not a statistician, but I'm a dynamical system person. So you'll see the trend in my talk. So this will be a little bit different from what you have seen before. The objective is to develop efficient methods in a multi-scale environment if I have multi-scale information. That is the purpose of this presentation. And I will try to thread three basic ideas. One is from random dynamical system, which is called a martingale problem. Martingale problem is what we will use in homogenization. Second idea has to do with nonlinear filtering, which is a stochastic partial differential equation, which comes from data-driven dynamical system. And the last part has to do with information flow, that is to do with mutual information between the posterior and the prior. That comes from information theory. So the whole purpose of this presentation or the method is to put together ideas to bring data assimilation to a lower dimension whenever you have multi-scale effects in the system. So since I saw so many presentations on tipping points, I would like to present something to begin with on random dynamical system, which has been an area of my research for almost 10-15 years. Then I will get into lower dimensional filters. I will do filters without tipping, therefore there's no gluing in my homogenization. And then I will talk about scaling and how filtering interacts. So you can't throw out terms. You may throw out terms which are small when it comes to homogenization, but when it comes to filtering, you have to make sure that doesn't have information that is useful in assimilation. So it's a very subtle and fine point. And the last one, of course, is to show how one can numerically put together and develop this nice system of particles. So what is a random dynamical system? I have a model of the system. This is a vector field given to you, and model of the system gives you a flow on a manifold. Then you have a noise that is given by the uncertainties in the system, and that is a metric dynamical system that flows on a probability space. You put them together, what you have is a co-cycle or a skew product flow, and that's what you get. You have, so that's pretty fast. So I have theta here is your way your noise goes around in the space of chance. Omega is your chance space, and this phi is your co-cycle. That's the way it tells you how the chance is moving along with your state. And what you have here is a skew product flow. That is what you want to have to make sure you have an invariant measure for this dynamical system. So every random dynamical system starts with an invariant measure. And I would like to know whether invariant measure is stable, unstable. If it is unstable, do we have a tipping point? So I will give you, without too much, this is a very simple Duffing van der Pol oscillator. I have two noises. I have removed the third noise, which is the additive noise. And I would like to show you the bifurcations that you can have in the system. So you have, this system has x is equal to 0 is a trivial solution. I have a delta measure at 0. That is a known measure. And then you look at the Lyapunov exponent of this measure, they are always negative, therefore they are asymptotically stable. Then you can see at this point D, I have a D bifurcation. It's a dynamic bifurcation where you have Lyapunov exponents crossing the imaginary axis. And you see one branch of invariant measure, mu, which is stable, which is branching off from there. The other one is still on the negative side. That becomes unstable here. You have an unstable invariant measure. And P is where you have, if you look at the density functions, you have a crater is formed at this particular point P. And there are two measures by which you can calculate D and P. One is called the Lyapunov exponent, other one is called the moment Lyapunov exponent. These are the two ingredients you need to define where the tipping points are in a random dynamical systems. So with this introduction, and to get these, we have to reduce our dimensions, center manifolds, all these things can be done. So now I come to the part of my real lecture.
Excuse me,
Yep.
because it's important for the rest of the talk.
Yes.
When you calculate the Lyapunov exponent, do you calculate it for the noise-free dynamical system
No.
or for the random dynamical
For random dynamics.
So you calculate it numerically?
No.
Okay.
For when you bring it to a lower dimension, you can calculate it through an integral.
Okay.
Right? So the Lyapunov exponent, this is a very interesting point. There are two. So if I draw the relationship between the Lyapunov exponent, can you see if I draw here?
Yes.
I have, this is called a moment Lyapunov exponent. That is your Lyapunov exponent. Usually the picture is like this, and that is your lambda, and that is your slope of the moment Lyapunov exponent at 0. So if you find the moment Lyapunov exponent, that includes within it Lyapunov exponent. It also contains the large deviation result as to how fast I can attain the Lyapunov exponent. So this is what you want. If you want to find, I think it was you who asked for metrics that you want to find. This is a metric that you would like to have, moment Lyapunov exponent. Okay.
Sorry, what's P here?
Huh? P is your moment, pth moment. So let me. So G of P is equal to limit T goes to infinity 1 over T log expected value xp. P is right. So let's come back to the real part of my presentation. Sorry, it takes some time. So I have now a system which is actually, I make the noise to be a VNAV process for simplicity. And I have a plant, this is my signal, I have a vector field V, and I have your uncertainties going to W. I have randomness in my initial conditions. I have randomness in my observation. There are 3 sets of randomness. And what I would like to understand is to estimate X with respect knowing what I have about Y. Y is the observation I have up to time T. So this is what the classical filtering theory provides you. And what you have is such 2 equations. One is called the Kushner equation. Other one is called a Zakai equation. These are the nonlinear versions of Kalman. Kalman is for linear, Kushner and Zakai for nonlinear. So if you can look at this carefully, you can see if I have no data, I will be propagating, my density function will go from here to here. If I have data, I will use the data to correct the density. Therefore, this is a data-driven dynamical system. What is propagating is conditional law. The conditional law is given by P, and the unnormalized density is given by U. So the advantage of dealing with U is given by a linear partial differential equation, whereas P is given by a nonlinear partial differential equation. the whole point I will talk about today is to see how one can solve these equations if I have multi-scale effects. Right. So I'm here for the climate problem, climate conference. So this is my prototypical model. I have ocean, I have atmosphere. I would like to eventually couple these things and solve and assimilate data. I'm interested in low order models, right? So my prototypical model contains a fast atmosphere. Epsilon is your scale parameter. And then I have X is my ocean model, that is slowly varying compared to atmosphere. And I have data coming from various sensors, and one of the sensors I picked here is MoCA. And y is a vector. I can have y can be a function of x, it can be a function of x and z. So this is your multi-scale information. So now I think I should also try to say here, z here is your noise. This is your stochastic parameterization of the system, and it doesn't have to be white. So what I would like to assume is that I will assume z to be given by some process. I can have any amount of noise I want in it. I can have, so I can create my z through a filter. Right? So this gives you the color I want in my system. If I want it to be colored, then I will go through a filter. But for the sake of simplicity, let's assume there's no color, at least in this presentation. So I'm going to come back here. So what I want to do actually is to combine. So what I want to combine here is this is classical equations, that is Kushner, Sakai, Kalyanpur. And this is what we have done a lot in random dynamical systems. Some of the work I did from 1995 to 2002 has to do with dimensional reduction with tipping points. Right? And if you put them together, what you have is reduced filters, which are much more efficient to work with. So these are the equations I will deal with. I have, and in some cases you can assume that sigma is zero. That is, most of my noise in my plant is only in the fast variable. The slow variable may not have noise. For example, Lawrence 96 is an example in which you have no noise in the slow dynamics. So we'll start. So the typical picture you see actually is I have my fast dynamics. This is my slow dynamics, which they are coupled together, and then I have my observation. Observation is going to be in green. So I have, these are Markov processes, because I'm assuming diffusive. I'm assuming Wiener processes as my noise. Each Markov process has its generator. The generator associated with the fast, I will put a subscript here, F is a generator for the fast dynamics, S is for the slow dynamics. Now I would like to ask, what is the probability of finding X and Z? This is exactly what, given the set A, given the information up to type T. And that is what we call conditional law, and that is given in terms of unnormalized density, and this is exactly what. So we want to basically solve this equation as easy as possible. If you want to find both X and Z, there is no simplification. The only simplification will be there is if you want to find the coarse grain dynamic. If I want to estimate X, that is, if I want to estimate ocean states in a decadal time, then I can tell you there is some possibility to reduce these dimensions to get some answers. So what I would like to ask is it possible to find the density or the conditional density just for x, given the information up to y, in a lower dimensional context? And that is a key. That is a key of this talk. So what I know actually is xt epsilon goes to x0. That is, there is a homogenization. And we have shown before that if we have this multi-scale dynamics, xt epsilon is my coupled nonlinear system. I can actually approximate xt epsilon by x0 rigorously. If that can go to there in a weak sense, does the filter go to here? And we want to show it does, with some bells and whistles. Right? So, and that's the question we want to ask. So the problem we have is just because x epsilon goes to x0 and the observation goes to something called y0 does not imply easily that the filter goes to. You have to work on it. So let me explain this through a very simple model as opposed to n dimension. Think in terms of these three equations. This will give you a pretty good idea as to what we are doing. I have theta, the fast process, is an angle. It's a Brownian angle. It's going very fast at a very high rate. X is your axial diffusion, and that depends on theta. This is a coupling. Right? And my observation depends on both theta and x. This is my multi-scale information. My information contains both scales. So what I want to know is what is the probability of x being in dx given y up to now time. Conditional law of my slow process. So you scratch your head. This is I'm not a mathematician. I'm an engineer. So you come with your own ideas how it works, and then you try to show it really right. So intuition sometimes pays. Good to be an engineer, all right? So you have good intuition, I suppose. So if you have this system, if you have theta which is going very fast, you can say, okay, let's average theta. Therefore, I have x0. This is my average system is equal to b bar. B bar is equal to some average of b, right? This is what I have b bar. It's a diffusion coefficient, so it has to be squared before you average it. And of course, I can average my y. I have an average information. I don't know what y0 is, but I can average it. The question we want to ask is, what is the filter for this? If somebody here gave me this plant and this observation, I can create a filter for this. And then that particular filter is going to be like this. Probability of xt0 belongs to this given this information. Okay, this is a filter for the homogenized system. This is the filter I start off with for the x. And I want to show somehow as epsilon goes to 0, this magically goes to that. And it is actually so the whole point actually is to show these equations can be solved, and this is I won't go. In fact, we can show indeed as epsilon goes to 0, this one goes to that. It's a lot of analysis. You can go to the paper. You can read it. So what I have actually is this. So if we take it back to my original problem, I had x and z. I can average it, homogenize it. I have averaged this. I get this equation. Therefore, I have now a filter of the average system, and my original filter goes to the system. But the problem I have is, what is y0? Y0 is something that I cooked up. Okay. I average my observation. You can't average observation. You're wasting information. Right? That actually is a problem. So the observations we have are given as y epsilon. Even though we would prefer y0, but I don't know. I mathematically is a y0, but I don't have it, right? This is an Air Force funded research, so we call it Rumsfeld dilemma, right? Let me paraphrase Rumsfeld. So you filter with observation you have, not with observations you might want or wish you have, right? Combining scales and filtering, you have to remember, the observation you have is y epsilon. What's observation that we have used in this filter is y0. And the question actually is, how do I come out of it? To come out of it, you have to understand filter is a mapping from the space of observations to the space of conditional law. Okay? The point actually is, can I replace my y0 by y epsilon, and still I can show. So what I have actually is, my filter is this is the original filter. This is what I have shown this to convert to this. Now I would like to ask whether I can replace this by y epsilon. Therefore I will get now pi 0 replace y0 by y epsilon, and then I show that indeed converges to that. So what I want to show here is this filter is close to this filter. This is tricky. So I homogenize my system, but I replace the real observation. Homogenize my system, I use the real observation as a mapping and show that filter that I have, this filter is close to this one. So the result actually is, so this result.
But wouldn't the dimensions be wrong?
No, dimensions are exactly same, because the filter is only the observations are the same dimension.
They're only observing the slow variable.
Yeah, all observations. Correct.
Yes, that actually raises a question I had before. When you
Go
have
ahead.
your square root term
Yes.
and you have your b squared, sometimes is it a b or a b transpose?
No, since in the example I showed you is a scalar.
Okay.
So the theta was a scalar, therefore b squared is fine. Otherwise, it would be b transpose.
And then that comes up with this arbitrary orthogonal matrix, which always rears its ugly head when we
No,
apply
because
it.
what I want is a measure. See, what I want is a conditional law. See, I'm not looking for, I cannot show a trajectory. This trajectory is almost surely same as this trajectory. That's impossible. Right?
No, you're looking for a weak convergence. I agree.
Weak convergence, what I have is a measure. So let me explain what I'm trying to say. So what I want to show is black quotes.
I think I've caught your point, so you don't have to waste your.
Yeah.
Okay.
So I want to show that, right? This is a generator.
Right.
And this contains sigma transpose of my original system. Then here this contains sigma transpose.
Right.
So this one converges to that, right? Therefore, the Markov process, in a weak sense, converges to that. That's actually basically homogenization, all right?
Right.
But what Chris was asking is, when you replace y epsilon by y, do you have any problem with dimensions? No, it's no problem with dimensions. I'm basically saying a filter is a mapping from the space of observations to conditional law. So I want to now replace my domain instead of y0 by y epsilon. That's what I'm doing. So what we can basically show actually is that you can, you have these two. This is now coming back to, so this is theory. So theory basically tells you that I can really show rigorously there is a lower dimensional partial differential equation which I can solve if I can to estimate the coarse grain dynamics given the information. So the question actually is, how do I do the particle method? So I would like to do two things here. I would like to do averaging or homogenization along with the particle methods I've used. So homogenization, of course, is what we have shown, and the hybrid part comes from Rumsfeld because I want to use the real information, right? So it's a hybrid because I'm not using y0, I'm using y epsilon. So this is, so particle methods, I think you have talked about it, and many people have talked about it. The only thing here is that I have to homogenize my weights. The homogenization of the weights had to be taken into consideration by looking at this integral. So this is a key to my homogenization. This homogenization tells you that I have my sensor function, which is homogenized, and therefore the weights have to be replaced along with the homogenization, and therefore you will have a straightforward convergence of the particle method. So I give it to a simple example here. I have an example here. I have Z. It's a very fast process. X doesn't have a noise, right? And I would like to estimate X given Y. And I have two different, the first one is a full particle method. There's no approximation. And that takes about 447 seconds. And for the same initial conditions, I can do with a hybrid particle method in 17 seconds. This is a reduction in the speed of nonlinear physics. And the last topic has to do with how many? I have one.
Couple of minutes.
So the last topic has to do with far from here. The question we want to ask is, how do I manipulate my senses? Knowing. So when you come from aeronautics, you can manipulate your sensors. They are UAVs. They're moving around. But in ocean, you have underwater vehicles that possibly can be also manipulated. What we want to ask is it possible to control your vehicle in order to get better information so that I can assimilate the data better and get better estimates? So here, I would like to bring in information theory to ask how one can look at the mutual information between the posterior and prior and look at the rates of information flow. And the rate of information flow is basically J. What we have basically got is a nice result showing that this is an extension of Zakai's results for the homogenized system. The rate at which the information changes is given by this formula, and this is handy in our calculation of our control. So I think let me put my conclusions here. You can read them, and I think I will stop here and let the chair ask for permission. Yeah, go ahead. I don't want to read it again.
Any further questions?
Yep.
Chris?
How would you summarise the conceptual and practical advantages of working in this continuous Zakai-Kushner framework, where you're assuming continuous stream of observations, compared with the more usual way that people do it in terms of sequential Bayesian filtering, which is perhaps easier to understand?
Most of the data we are collecting, this project started with electric power systems, in which we are getting, in a second, we have about 20, 30, 40 data points. So it's almost like a continuous slew of information. So this is a framework in which we would like to do those problems. So the only thing is it makes the mathematics interesting and difficult, but it allows us to also go into the deeper side of information science. Yeah. The point actually is if we can collect data very fast, then you can use these ideas to look at continuous time filters.
Last question from Tim.
Just a comment, actually. It was about, well, actually, this bit at the very end of your talk about sort of adaptive observations type thing. I mean, I mentioned in my talk on Monday that von Neumann's idea of using weather forecasts was actually to modify the weather. But there's a variant of this which has become kind of the topic of a number of field campaigns in recent years, which is to calculate kind of finite, if you like, finite time Lyapunov vectors for an atmospheric model, and to determine, you know, where in the atmosphere particular sort of localized areas of instability
Sure.
might occur,
Sure.
and then send pilotless drones and adaptive observations to do detailed measurements in those areas.
Precisely, yeah.
Um,
So they actually, in a way,
the design of the observing system around the instabilities
sure.
of the
You're
flow.
trying to find the finite time exponents, find the largest one towards which you want to send the
Exactly,
pilot.
yes.
Precisely. In a way, it has some of these relevance.
Yeah. So there
But
are some programs in meteorology which are trying to
I
do
see.
that. As I say.
But here I'm actually going one step further and asking, I would like to look at the posterior and a prior and decide on that how to create my control algorithm. That is it. Yeah, it has some. Thank you. Yeah.
Okay, thank you. We have a break now for coffee. We start again promptly at 11:30, and we'll have Rachel Warren as the first. Yeah, got that right. First to talk, and then Magna Aldrin in that order. Thanks again, Street.